This lecture is about the sentiment classification. If we assume that most of the elements in the opinion representation are already known, then our only task may be just the sentiment classification, as shown in this case. So suppose we know who is the opinion holder and what's the opinion target, and also know the content and context of the opinion. Then we mainly need to decide the opinion sentiment of the review. So this is a case of just using sentiment classification for understanding opinion. Sentiment classification can be defined more specifically as follows. The input is an opinionated text object. The output is typically a sentiment label or sentiment tag, and that can be designed in two ways. One is polarity analysis, where we have categories such as positive, negative, or neutral. The other is emotion analysis. That can go beyond polarity to characterize the feeling of the opinion holder. In the case of polarity analysis, we sometimes also have numerical ratings, as you often see in some reviews on the web. 5 might denote the most positive, and 1 may be most negative, for example. In general, you have just discrete categories to characterize the sentiment. In emotion analysis, of course, there are also different ways to design the categories. The 6 most frequently used categories are happy, sad, fearful, angry, surprised, and disgusted. So as you can see, the task is essentially a classification task or categorization task, as we have seen before. So it's a special case of text categorization. This also means any text categorization method can be used to do sentiment classification. Now, of course, if you just do that, the accuracy may not be good, because sentiment classification does require some improvement over regular text categorization technique or a simple text categorization technique. In particular, it needs 2 kinds of improvements. One is to use more sophisticated features that may be more appropriate for sentiment tagging, as I will discuss in a moment. The other is to consider the order of these categories, and especially in polarity analysis, it's very clear there's an order here, and so these categories are not all that independent. There's order among them, and so it's useful to consider the order. For example, we could use ordinal regression to do that, and that's something that we'll talk more about later. So now let's talk about some features that are often very useful for text categorization and text mining in general, but some of them are especially also needed for sentiment analysis. So let's start from the simplest one, which is character n-grams. You can just have a sequence of characters as a unit, and they can be mixed with different ends, different lengths, right? And this is a very general way and very robust way to represent the text data. And you can do that for any language, pretty much. And this is also robust to spelling errors or recognition errors, right? So if you misspell a word by 1 character, and this representation actually would allow you to match this word when it occurs in the text correctly, right? So misspelled word and the correct form can be matched because they contain some common n-grams of characters. But of course, such a representation would not be as discriminative as words. So next we have word n-grams, a sequence of words. And again, we can mix them with different lengths. Unigrams are actually often very effective for a lot of text processing tasks, and it's mostly because words are well-designed features by humans for communication. And so they are often good enough for many tasks, but it's not good or not sufficient for sentiment analysis clearly. For example, we might see a sentence like, it's not good, or it's not as good as something else, right? So in such a case, if you just take a good, and that would suggest positive, that's not good, right? So it's not accurate. But if you take the bigram, not good together, and then it's more accurate. So longer n-grams are generally more discriminative, and they're more specific. if you match it and it says a lot and it's accurate, it's unlikely very ambiguous. But it may cause overfitting, because with such very unique features, the machine learning program can easily pick up such features from the training set and to rely on such unique features to distinguish categories. And obviously that kind of classifier won't generalize well to future data when such discriminative features will not necessarily occur. So that's a problem of overfitting. That's not desirable. We can also consider part-of-speech tag n-grams if we can do part-of-speech tagging. And for example, adjective noun could form a pair. We can also mix n-grams of words and n-grams of part-of-speech tags. For example, the word great might be followed by a noun, and this could become a feature, a hybrid feature that could be useful for sentiment analysis. So next, we can also have word classes. So these classes can be syntactic, like a part-of-speech tags, or could be semantic, and they might represent concepts in the thesaurus or ontology, like a word net. Or they can be recognized named entities, like people or place. And these categories can be used to enrich the representation as additional features. We can also learn word clusters empirically. For example, we've talked about the mining associations of words, and so we can have cluster of paradigmatically related words or synagmatically related words, and these clusters can be features to supplement the word-based representation. Furthermore, we can also have frequent patterns in text, and these could be frequent word set. The words that form a pattern do not necessarily occur together or next to each other, but we also have collocations where the words might occur more closely together. And such patterns provide more discriminative features than words, obviously, and they may also generalize better than just the regular n-grams because they are frequent. So you can expect them to occur also in test data. So they have a lot of advantages, but they might still face the problem of overfitting as the features become more complex. This is a problem in general. And the same is true for parse tree-based features, where you can use a parse tree to derive features such as frequent subtrees or paths, and those are even more discriminative, but they also are more likely to cause overfitting. And in general, pattern discovery algorithms are very useful for feature construction because they allow us to search in a larger space of possible features that are more complex than words that are sometimes useful. So in general, natural language processing is very important to derive complex features, and they can enrich text representation. So for example, this is a simple sentence that I showed you a long time ago and in another lecture. So from these words, we can only derive simple word n-grams representations or character n-grams. But with NLP, we can enrich the representation with a lot of other information, such as part-of-speech tags, parse trees or entities, or even speech act. Now, with such enriched information, of course, then we can generate a lot of other features, more complex features, like mixed grams of a word and part-of-speech tags, or even a part of a parse tree. So in general, feature design actually affects categorization accuracy significantly, and it's a very important part of any machine learning application. In general, I think it will be most effective if you can combine machine learning, error analysis, and domain knowledge in designing features. So first, you want to use domain knowledge, your understanding of the problem to design seed features. And you can also define a basic feature space with a lot of possible features for the machine learning program to work on. And machine learning can be applied to select the most effective features or construct new features. That's feature learning. And these features can then be further analyzed by humans through error analysis. And you can look at the categorization errors and then further analyze what features can help you recover from those errors, or what features cause overfitting and cause those errors. And so this can lead to feature validation that would revise the feature set. And then you can iterate and we might consider using a different feature space. So NLP enriches text representation, as I just said, and because it enriches the feature space, it allows much larger search space of features, and there are also many meaningful features that can be very useful for a lot of tasks. But be careful not to use a lot of complicated features because it can cause overfitting, or otherwise you have to do the training carefully not to let overfitting happen. So a main challenge in design features, a common challenge, is to optimize the trade-off between exhaustivity and specificity. And this trade-off turns out to be very difficult. Now, exhaustivity means we want the features to actually have high coverage of a lot of documents. And so in that sense, you want the features to be frequent. Specificity requires the feature to be discriminative, so naturally infrequent features tend to be more discriminative. So this really caused a trade-off between frequent versus infrequent features. And that's why feature design is generally art, and that's perhaps the most important part in applying machine learning to any problem, in particular in our case for text categorization, or more specifically sentiment classification.